In this video, we introduce the first derivative test for identifying the local extrema of a function, and then we apply the first derivative test to 5 quick examples. So the goal is to learn how to identify the locations of local minima and maxima purely by studying the first derivative of a function when we're given its formula. And we're going to stay sort of informal and geometrically grounded in our approach this time, so we're going to develop our first derivative test by just studying the graph of an example function which I called f of x. So we've already discovered that when we're looking for local maxima and minima, we want to focus on the so-called critical points of the function. And these are the points where the first derivative is either 0 or does not exist. So there's our critical points for f of x, and just as a reminder, these critical points are actually x values in the domain of f, and so I've called those C1, C2, and C3. And we see that at C1, we have a point where the derivative is 0. At C2, the derivative doesn't exist because I have a different derivative value as I approach that point from the left and the right. In other words, there's a cusp there. And then again at C3, we have a point where the derivative is 0. So we can tell by looking at the graph that C1 is the location of a local maximum, C2 is the location of a local minimum, and f doesn't have a maximum or minimum at C3, but our goal is to figure out an analytical test to confirm this rather than relying on the graph. So we start by studying the first derivative in a neighborhood of each critical point. Starting with C1, just to the left of that point, we can place a tangent line there and we see that it has a positive slope. In other words, the derivative of f is positive just to the left of C1, and this means f is increasing as I approach my critical point. Now just to the right of C1, I get the opposite result. My tangent line has a negative slope, the derivative is negative, and the function is decreasing. So at the critical point C1, our function makes a transition from increasing to decreasing. And if a function is switching from going up to going down, we must hit the top of a hill there. In other words, that's a local maximum. So this is actually what we're going to look for analytically. If we can see that the sign of the derivative changes from positive to negative as I cross a critical point, then I automatically know I'm looking at a local maximum. Let's continue this idea with our next critical point. If I go a little bit to the left of C2 and I draw a tangent line to the curve there, that tangent line is going to have a negative slope. That means the derivative's negative, the function is decreasing. When we repeat this a little bit to the right of C2, I see a positive slope on my tangent line. That's a positive value of f prime of x. The function is increasing. And we make the same sort of reasoning here. As I'm moving left to right, if my function is decreasing on the way into this point and increasing on the way out, then at that critical point, we must be hitting a local minimum. Finally, we look at this odd point C3. That doesn't appear to be a local minimum or a local maximum, and yet the derivative is 0 there. If we look to the left of that point, I see that the derivative is always positive. In other words, the function is increasing. And I look to the right of that point, and the tangent line has a positive slope again. So the function just continues to increase to the right of C3. So we're increasing coming into that point C3, and we're increasing coming out of it. And without that sign change in the derivative, that change between increasing and decreasing or vice versa, we're not going to have a local extremum at that point. So now we have the idea of the first derivative test nailed down. To systematically determine local extrema of a function, we're going to find the critical points and then check if the sign of the derivative is changing left and right of each critical point. And then we can classify each one of these as a local minimum, local maximum, or neither one of these in a case like C3. And the whole point of this is that now we can identify local extrema by studying the formula for a function rather than relying on a detailed plot of the function to assist us. In other words, we've found an analytical approach to the search for local extrema. So here's our formal statement of the first derivative test. So as our assumption here, we're told to suppose we have a continuous function on an interval I containing a critical point C, and our function is differentiable on that interval. So we're just thinking of like a neighborhood of a critical point. It's differentiable on that interval except for possibly at C where the derivative might be undefined, like in the case of a cusp. And we have 3 possible conclusions of the first derivative test. If f prime changes from positive to negative, then we're talking about a local maximum. If f prime changes from negative to positive, we have a local minimum. And if f prime doesn't change sign to the left and right of C, then we have no local extremum at C. So as you're reading through this test, you really want to avoid thinking of it as a memorization task. I've seen a lot of mnemonics out there where students are trying to memorize what sign changes in f prime result in what types of extrema, but you're going to do a lot better if you just think of this as a description of a picture. So just back at this picture where we have a local max and a local min, and one of the points that's neither a local max or a local min, we can see clearly around C1 that if I change from going up to going down, I must have got to the top of the hill. So that's a local maximum. If I change from going down to going up, like what's happening around C2, that has to be the bottom of a valley. In other words, a local minimum. And if I'm going up and then I level off briefly and then just keep going up, well, then I'm not at the top of a hill or the bottom of a valley. So this is really just an intuitive geometric fact. This formal statement of the first derivative test might look really complex, but we're really just expressing something that's very geometrically intuitive. So now we're ready to apply the first derivative test to several examples. Our first example is the simplest parabola. And again, what we're trying to do here is identify all the local extrema just by manipulating the formula for the function and its derivative, but we will verify with a graph when we're done with that. So I have f of x equals x squared. The first thing I'm going to do to search for critical points is compute f prime of x. And f prime of x is 2x. I want to know where that first derivative is 0 or undefined. Well, there's no point that's going to make it undefined, but it could be 0. And that happens when 2x is equal to 0, which happens when x is 0. All right, so that's our only critical point for this function. So now we have to figure out if there's a sign change in the derivative at this critical point. And it's not too hard to figure out in this case. If x is less than 0, then f prime is going to be less than 0. In other words, if x is negative and I take 2x, I get a negative number, so f prime is less than 0. And if x is greater than 0, well, 2x is also going to be greater than 0, so f prime, the first derivative, is going to be greater than 0. So to the left of our critical point, our function is decreasing. It has a negative derivative. And to the right of the critical point, our function is increasing. And this means we're looking at a local minimum. Now in the instructions to the problem, we're also asked to compute the local maximum and minimum values. So that means like the y values connected to these critical points. So our local minimum value here is just f of 0, and that's 0. Okay, so we've discovered that the point 0, 0 is a local minimum of the function f of x equals x squared. And you may be so familiar with this graph that you already guessed that before we even had to do any work. But there's the graph verifying that we have the bottom of a valley sitting right there at the origin for this function. In our second example, we have a cubic function, and we're trying to find the local extrema for this thing. And again, we start by taking the first derivative. That's going to be 3x squared minus 2x minus 1. And we're going to set that equal to 0 and try to solve for those critical numbers that make the derivative vanish. So what we're hoping for here is that this thing is factorable. If it's not, you're going to have to use the quadratic formula, and then the problem starts to get really ugly. And fortunately, I rigged this one to factor, like so many of the calculus books do. If it factors into two binomials. One of them will start with 3x and the other one starts with x. Then it's a guess and check game of how to tweak the constants to make the cross term work out here. Well, those constants have to have a magnitude of 1. And then I just had to pick the plus and minus signs correctly. So my cross term is a negative 2x. I think having a negative 3x is going to help me here. So when I take this product, 3x times negative 1, I get negative 3x. If I make this one positive, I'm going to get a plus 1x, giving me a net negative 2x. So factoring really is a guess and check process. And it's just a matter of practice, moving the pieces around and then just checking by using FOIL, hopefully in your head, until you find the right combination to factor this thing. So I'm thinking through FOIL here, and I have 3x squared minus 3x plus x. That gives me the right cross term, and then minus 1 at the end, so everything's working great. So I'm left with this equation, 3x plus 1 times x minus 1 is equal to 0. And there's two ways to have a solution to that equation. Either one of these factors could be equal to 0, and because 0 times anything is 0, that's going to be a solution to the equation. So I get one solution when 3x plus 1 is 0. I subtract 1 and divide by 3, and I find that x is equal to negative 1/3. And I get another solution when x minus 1 is equal to 0. Adding 1 to both sides, that means x is equal to 1. So those are our critical points for this cubic function. I have two of them. And now I have to figure out how the sign of the first derivative is changing as I cross over each of these critical points. Now there's a nice tool we can use for keeping track of everything when I have more than one critical point. And the idea is to just look at a number line here and then mark the critical points on a number line. So I have -1/3 and I have 1. And I'm trying to figure out the sign of the derivative. So this expression right here, 3x plus 1 times x minus 1 is f prime of x. I'm trying to figure out what the sign of that thing is in these three different regions. So to the left of -1/3. There's a couple ways to approach this. You could just pick some arbitrary number over there to the left of -1/3. Like for example, I could put a -1 into the expression for f prime. And when I do that, I get a -2 for this first binomial and a -2 for the second binomial, giving me a positive result. So I know f prime is positive in that region. Again, we're looking at the sign of f prime on this number line. But you can be less specific than plugging in like one particular test point if you want. I can look at this first binomial and say, oh, when x is less than -1/3, 3x is going to be less than -1, making my first term negative. And because x is negative, x minus 1 is also negative, so I get a positive f prime. Same type of reasoning on this in-between region. You could plug in a specific number if you want, or you can just look at the signs of each of these binomial factors, knowing that x is bigger than -1/3. With x bigger than -1/3, that means 3x plus 1 is going to be a positive number. X minus 1 is still a negative number in this region, and so I end up with a negative result for f prime. If you don't like thinking about it that way, you can just explicitly plug in x equals 0 as a test point here, and I would end up with 1 times -1, which is -1, so f prime is negative in this region. Now finally, to the right of 1, x minus 1 is clearly positive, 3x plus 1 clearly positive, and f prime as a result is also positive. So to the left of -1/3, our function is increasing. It has a positive derivative. To the right of -1/3, it's decreasing. That means there must be a local max at that value of x. And again, this doesn't have to be a tedious memorization task. I'm just visualizing that I have a function that's rising to the left of this point and then falling to the right of this point, which automatically puts this point at the top of a hill. Now when I'm at x equals 1, I'm switching from decreasing, so the function is decreasing or going downward to the left of that point, and then switches to going upward, which puts it at the bottom of a valley. That's a minimum right there, a local minimum. So I have a local maximum at x equals -1/3 and a local min at x equals 1. And here's where things can get a little bit tedious. Again, I've been asked to find the local maximum and minimum values, and this means I need to find the value of f at x equals -1/3 to get that local maximum value. Well, that's going to take a little bit of work because I'm plugging -1/3 into a cubic function. So x cubed, that's the first term in our function, is going to give me a -1/27. Then I have minus x squared. X squared is 1/9. And then minus x, which will give me a plus 1/3, and then plus 1. Our common denominator there is going to be 27. So I have -1/27 minus 3/27 plus 9/27 plus 27/27. Adding all those up, I have a -4/27 plus 9/27. That's 5/27. Then I add that to 27/27, and I end up with 32/27. In other words, a number slightly bigger than 1 for my local maximum value there. The local minimum value is a really easy question. If I sub in f of 1, I end up with 1 in the first term, minus 1 for the second term, minus another 1 for the third term. That gives me a -1, and then I add 1 to it, and I get 0. So my local minimum value there is 0. Finally, we bring in a graph of the function, and we look at these two local extrema, one right here and one right here. And we see that local minimum clearly occurs at 1, 0. And we're just approximating for the local maximum, but it looks plausible that it's x equals -1/3, and then the y value corresponding to that, again, is slightly bigger than 1. In our next example, we have an absolute value function. Now, you might remember that these come with a cusp. So this time we're looking for a critical point where the derivative doesn't exist. Now, sometimes we're given an absolute value function in this form, and sometimes we're just given the piecewise defined version of it. So what I want to do is take this function, f of x equals negative absolute value, x minus 3 plus 2, and turn it into a piecewise defined function. And then we're going to show the derivative doesn't exist at one particular point. And then we'll do our first derivative test and find our local extremum. So the reason this produces a piecewise defined function is because the absolute value function switches its behavior depending on whether its argument is positive or negative. So if x minus 3 happens to be greater than 0, or equal to 0, in fact, the absolute value is going to do nothing. It does nothing to non-negative numbers. All right, then this will mean that f of x is the negative of x minus 3 plus 2. The absolute value bars did nothing there. So I end up with a nice formula for f of x, provided x minus 3 is bigger than or equal to 0. And that's negative x. And distributing my minus sign here, I end up with a plus 3 and then a plus 2. So negative x plus 5. And again, this is occurring only if x minus 3 is greater than or equal to 0, which is totally equivalent to saying x is greater than or equal to 3. So that's the first piece of our piecewise defined function. Now, if x minus 3 is less than 0, the absolute value function is going to multiply it by negative 1 to turn it into a positive number. So I have the negative of the absolute value of x minus 3, but the absolute value of x minus 3 is the negative of x minus 3. So I end up with a positive x minus 3 plus 2. That cleans up to x minus 1, just a simple linear function with a positive slope. And this is going to occur when x is less than 3. So writing f as a piecewise defined function, I have the formula x minus 1 when x is less than 3, the formula negative x plus 5 when x is greater than or equal to 3. And now we can look for a point where the derivative is not defined. So if I'm not at the point x equals 3, the slope of this thing is going to be well defined. When x is less than 3, I have a slope of 1. That's just the derivative of x minus 1. And then if I'm to the right of 3, I have a slope of negative 1. It's just the derivative of negative x plus 5. But at that one point, x equals 3, as I'm approaching that point from the left, again, I have a slope of 1. As I'm approaching that point from the right, I have a slope of negative 1. So the two limits that I need to agree for the derivative to exist, they're disagreeing with each other. The slope is different from the left and the right, and f prime of x does not exist when x is equal to 3. I could have also just said f prime of 3 does not exist. So that means x equals 3 is our critical point for the problem. Now I need to look for a sign change in the derivative. And we've already sort of figured this out. When x is less than 3, f prime of x is going to be positive 1. And when x is greater than or equal to 3, f prime of x is negative 1. So there's my sign change. I have a sign change from a positive derivative to a negative derivative at this critical point, making it a local maximum. So we can plot the function and we see a local maximum occurring at x equals 3. The one thing I forgot to do before pulling in the graph was to find the local maximum value. So you would obtain that by just subbing in x equals 3 into the formula for f of x. So when I look at this rule, which counts for x greater than or equal to 3, I sub in a 3 to that, I get negative 3 plus 5. That's a vertical value of 2, which is the same thing I see in the graph. In our next example, we have a trig function. So I have f of x equals 2 sine x on this closed interval 0 to 2 pi. So we take the derivative and set it equal to 0. And the derivative is 2 cosine x. So we're going to set that equal to 0. And now we're just looking for values of x that make the cosine function 0 on 0 to 2 pi. Well, this occurs when x is equal to pi over 2. In other words, straight up on the unit circle, I have an x coordinate of 0. So the cosine vanishes there. And it also happens at 3 pi over 2, straight down on the unit circle, again giving me an x coordinate of 0, so the cosine function vanishes. So now I have to think about sign changes in the derivative. So I'm going to use that number line idea again. And I'm really just visualizing the unit circle as I make these decisions. If I have an x value that's between 0 and pi over 2, that puts me in the first quadrant. And the cosine function is positive there. In other words, the x coordinate of a point on the unit circle is positive in the first quadrant. So with the cosine being positive, that means f prime is positive. And I figured that one out. Now between pi over 2 and 3 pi over 2, we're on the left half of the unit circle where I have negative x coordinates. In other words, the cosine's negative there. So that's figured out. And then again, as I go beyond 3 pi over 2, I'm in the fourth quadrant. I have positive x coordinates for a point on the unit circle. The cosine has a positive value, so f prime is positive. So that's all figured out. And I noticed that at pi over 2, I have a transition from positive to negative, making that a local maximum. I also want to find that local maximum value. So f of pi over 2. I go back and sub in pi over 2 to my original function. And the sine of pi over 2 is 1. So I end up with a local maximum value of 2. Next, I have a local minimum at x equals 3 pi over 2, because that's a transition from decreasing to increasing. And my local minimum value is going to be an f of 3 pi over 2. Well, the sine of 3 pi over 2 is -1, so I end up with -2 for this. So bringing in a graph of the function, we see that all this works out. At pi over 2, I have my local maximum value of 2, and at 3 pi over 2, I have my local minimum value of -2. Finally, we get an interesting function that's kind of a mixture between a polynomial and a trig function, so x plus sine x, and we're restricting our search to the interval 0 to 2 pi. So we take the derivative of this thing, and we get f prime of x is equal to 1 plus cosine x, and we're interested in where that is equal to 0. So I'm trying to solve 1 plus cosine x equals 0. And that means the cosine of x is -1. So you could express x as an inverse cosine of -1, but at some point you're going to have to guess the x value that makes the cosine equal -1. And again, this is just visualization of the unit circle. Where do I get an x coordinate of -1 on the unit circle? And it's when I'm all the way on the left of the unit circle at an angle of pi. So x is equal to pi here. So in general, there are infinitely many x's that satisfy that equation, but we're restricting ourselves to this interval. So that's why there's only one solution at x equals pi. So that's our critical point. Now we want to think about the sign of the derivative around that point. So what if x is a little bit less than pi? So we have an angle just a little bit less than pi. Well, that still puts us in the second quadrant on the unit circle. So I'm just slightly above an angle of pi, and the x coordinate is still negative. In other words, the cosine is still negative there. And if I go a little beyond an angle of pi, so I'm dipping into the third quadrant now on the unit circle, the value of cosine is still negative there as well. All right, so these are negative values that have a magnitude less than 1. Well, with f prime being 1 plus cosine x, and cosine being negative but having a magnitude less than 1, 1 plus cosine x is always going to be a positive thing. So I have f prime greater than 0 if I'm a little bit left of pi. In other words, a little before pi on the unit circle, if you want to visualize it that way. And I have f prime being greater than 0 a little bit right of pi, or a little beyond an angle of pi on the unit circle. So we finally get to see a case where we found a critical point, that's x equals pi, but we didn't have a sign change in the derivative. So this is not a local maximum or a local minimum. And bringing in a plot of our function, our critical point was at pi, that's slightly bigger than 3, and I see a flat spot in our function there. So I have a spot where the tangent line is horizontal, but my function is increasing to the left of that and increasing to the right of that, so I have no local maximum or local minimum. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.